Hello, and thank you for joining me today. Today we're going to look at writing nuclear equations, and we're going to actually do the equations and the solving for alpha, beta, gamma, positron emission, and electron capture. So this is going to be a comparison of your different types of decay, along with using them in nuclear equations. So at the end of this video, you'll be able to compare alpha, beta, and gamma radiation in terms of whether they're particles or waves, the speed of the particles, the size of the particles, and their ability to penetrate a substance or material. You'll also be able to recognize, write, and balance your basic nuclear equations for alpha, beta, and gamma, along with positron emission and electron capture. So this is the goal for today. And here we go. So for starters, alpha, beta, and gamma can be compared in a number of ways. So what they are as particles, your alpha particle is a helium nucleus, which we talked about in the last video. Your beta particle is an electron, high-speed and high-energy electron coming from the nucleus, and your gamma radiation is energy. Your charge, because it's got two protons, your alpha particle is a positive 2. Because it's an electron from the nucleus, your charge is -1 for a beta particle, and energy doesn't have a charge. Mass, because it's two protons and two neutrons, comparatively, the mass of your alpha particle is going to be very large. A beta particle is relatively small, and then energy doesn't have mass, so there's your gamma radiation. Because these are big, it's going to be slower. Medium is going to be a little bit faster. Because there's no mass at all, it's just energy. We're moving at the speed of light, so this is really fast. And everything kind of goes accordingly. So because it moves slow, it's very strong. It has a very strong ionization effect, or an ionizing effect. Because beta particles move faster, it's got a weaker ionizing ability, and energy doesn't have much of an ionizing ability at all. Because these are big, they don't penetrate very much, so alpha particles aren't really dangerous to you unless they're inside your body. So if you would ingest something that's undergoing alpha decay, then you're in trouble. Otherwise, on the outside, your skin can pretty much block alpha particles from entering and causing any damage. Beta particles are able to penetrate your skin. They're dangerous on the outside, so you need a little bit of a covering. Gamma radiation, if you think of the Hulk, you need a lot of protection when dealing with gamma radiation. So this is very dangerous even outside the body. And here's kind of a comparison. So here's your symbols, alpha, beta, and gamma we talked about in the last video. Mass is roughly 4 AMUs, 2 protons, 2 neutrons. Beta particles are effectively 0. 1/2000 is effectively 0, but it's very small. And then gamma is absolutely 0. It's just energy. Again, low penetration for alpha particles, intermediate for beta, very high for gamma. Ionizing power, again, because low penetration, high ionizing, intermediate's there, high becomes low. To protect yourself, alpha particles, your skin can protect you from alpha particles, or a piece of paper can stop an alpha particle. If it's beta, you need something like aluminum to slow it down and stop it. If we're talking gamma particles, this is where you need not just a little bit of lead, but actually 2 inches of lead. So gamma radiation has a very strong penetration ability. Penetrates very well, so you need a lot of protection from gamma particles, gamma radiation. Here's kind of a comparison chart. This would be a good one maybe to have down, to be familiar with. This will help you out a lot when you look at nuclear decay and equations. If you write this table down, this would help you out, I think, immensely. So alpha particle symbol is here. Your beta particle is 0, -1, or you can write it as E, 0, -1. Remember, gamma is just energy, so we use the Y. A positron is a beta particle with a positive charge. And then electron capture is the same as a beta particle. You can write the beta particle, or you can write the electron. But those are your symbols for these different types of decay. This tells you your change in protons. So if you undergo alpha decay, your protons change, they go down by 2. If you undergo beta decay, you gain a proton because you picked up, you released the beta particle, which means you had to gain a proton. A neutron became a proton to release this particle. Gamma doesn't change anything. A positron emission, your proton became a neutron. An electron capture, again, proton became a neutron. So your neutrons in this case, we lost 2 protons. We also lost 2 neutrons for alpha. instead of gaining a proton, because I gained a proton, I lost a neutron. Again, gamma is nothing. I lost a proton, meaning I gained a neutron. I lost a proton here, meaning I gained a neutron there. And then mass-wise, the only time we change mass is with alpha decay with our 4, which is good to know. All right, so let's do some practice. I want you to write the nuclear equation for alpha emission by polonium-210 used in radiation therapy. And so if we look at this, we know that polonium has a mass of 210. PO. Let me grab my periodic table quick. But we know that polonium has a mass of 210 and it's going to undergo alpha decay. So I know on this side I'm going to have 4 over 2 He plus here. And then my atomic number for polonium is going to end up being I apologize, I should have had this out earlier. Okay, Google, what's the atomic number for polonium?
Polonium has atomic number of 84.
So polonium's atomic number is 84, so I should have an 84 here. And so on this, we're going to end up with A over Z and X. We got to figure out what A and Z are. So I know that 210 equals 4 plus A, which means that A equals, I'm going to subtract 4 on both sides, 206. I know 84 equals 2 plus Z. I'm going to subtract 2 on both sides, so I know that Z equals 82. So this is going to be 210 over 84. Polonium produces 206 over 82. And 82, I believe, is bismuth. Nope, it's not bismuth. 82 is lead. Plus my alpha particle, which is He 4 over 2. It does not matter if you write the alpha particle first or last. I tend to write the nuclide first. It's just how I do it. Okay, so this is alpha decay. I'm going to have you try beta for gold. So do it the same way. So gold 198. So you have Au 198. And it undergoes beta emission. So remember, beta decay is going to be 0, negative 1, B. And you're going to solve for your numbers here. Positron emission by nitrogen 12. So you have N12. Nitrogen's number 7. Positron emission, meaning I'm going to have something plus 0 over positive 1. Beta particle, and electron capture. So the difference between beta emission and electron capture is the side. So I have gallium, Ga67, because I'm capturing it, 0, negative 1 beta particle, and then your answers should be on the other side. So work through these. I'll have your answers on the next slide, and I'll give you some more that you can practice on your own. So pause this video, work through those. When you hit play, you'll get your answer. So here's your answers. So beta emission by gold. So gold goes from 198 and it will decay into mercury 198. Nitrogen 12 becomes carbon 12, undergoing positron emission. Gallium 67 becomes zinc 67 after it undergoes electron capture. So those are your first 3 that you worked through. Here are some more for you to practice. So write your equations for the alpha emission of plutonium 239 I want the beta emission of sodium 24, positron emission of oxygen 15, electron capture of copper 64. Pause this video, work through those. I'll give you the answers on the next slide. So here are your answers. Check your work. If you have questions, please let me know. Again, in this situation, we have neon with a little asterisk. This just means it's a high energy neon atom. So this one's going to undergo alpha or gamma radiation shortly after it's formed. So this is going to release a gamma particle, which is just losing energy to stay neon 22. But these are your answers from the last set. And then I have one more set of practice questions for you to try. So fill in the blanks here. So Glenn Seaborg and his team of scientists at the Lawrence Lab at UCLA and Berkeley created a number of new elements, some of which berkelium, californium, lawrencium have been named in honor of their work. This is their process. So complete the following nuclear equations that describe the processes used to create these elements. This is how they were created. So work through these, fill in the blanks. Remember, all you're doing, make sure you add up your numbers on top and bottom and make sure they're equal. If you get stuck, come see me tomorrow and we'll talk through things. But give this a shot and see how we do. And here are your answers there. If you struggled with this one here, that's not a big deal. I understand if you had 12/6 and called it carbon 12. That's fine. Just understanding we're talking alpha particles is what they got hit with, and that's not a big deal. I'm not too concerned about that. All right, here's some review questions for you to work through. If you have questions on these, please come see me. If not, I do appreciate your time and attention. I look forward to finishing up this unit with you here shortly.